So now what we have done is we have built in module 4, we have learned how to build any arbitrary combinational circuit, right? How to build any Boolean logic, design it with various styles of logic so that we can meet certain specification. We can make it faster, slower, whatever it is, right? Lower power. We learned many techniques to design combinational blocks. Now in this module, we have designed all the sequential elements that we needed. Latches, flops, what is the setup time, hold time. So right now, what we have is, we have combinational blocks, blocks that have a delay TCD, that is contamination delay, right, and a propagation delay, right? We can characterize this and figure out what the two delays are, right? Then I have sequential elements which have, so let's only deal with a flop for now, okay? So we have TCCQ, TPCQ, right, T setup and T hold. So I can design these elements and hand them over to you and tell you that you have to now put these things together in order to make the system function at a particular clock speed. Our aim now is to determine what the maximum clock speed is, what is the minimum clock speed, right? Is there any minimum delay constraint? What is the maximum delay constraint? All of that we will study in over the next 2 days. Okay. So let us start with a basic flop based system, and I'll call it system delay. Constraints, right? So I have a flop with a clock 5. This is going to go through a combinational block, okay, and we're going to come and sit here with another flop, okay. The left flop is called a launch flop, the right flop is called a capture flop, okay. So I have D, Q1, D1, Q1, T2 and Q2. So right now I am assuming that the clock period is given to me. I have a clock period and the time period is TC. Okay, so let's assume that the clock is like this. Okay. Now I want to find out what is the, this is TPD, TCD. What is the maximum delay that I can insert between these two flops so that this system will not fail? What is the combinational block and what is the maximum delay of that combinational block that I can insert between these two flops so that the system doesn't fail? Okay. So what are these flops doing? These flops, they are memory elements, but here they are not playing just the role of a memory element. Their aim is not just to store something. Their aim is to sequence events. You launch some data, it has to calculate something, that flop has to capture that particular event and hold it for the next guy to do. So the events get sequenced as 1, 2, 3 and so on, and no event should get missed. Okay, that's the aim of putting it, you know, in a system with a flop, launch flop and a capture flop and so on. Okay, so let's see what happens. I have a change in D, in D1, that's happening here, right? So after the clock Q1, right, I mean after the clock rises, right, at 5, Q1 will change after, yeah, so So now I will do this. Okay, Q1 from the clock edge. This is what? TCCQ. What does this mean? It means if the data had changed well before the clock edge, then this would have been the delay. I don't know when the data is changing, right? I have to account for worst case under all conditions. That's what the analysis is going to be all about. Now, this guy will change worst case. What is this delay? TPCQ, right? Okay. So now what do? I am going to look at D2. D2 is going through D2 is the output of the combinational block, right? So the moment Q1 starts changing, right, they can be the earliest change that happens at the output of the combinational block, which is the contamination delay of that block, right, which will be determined by the shortest path of change, right? So D2 will have another similar structure here, right, where you have some changes like this. From here, you will have, what is this delay? TCD, contamination delay of the combinational block. And this guy will be TPD. Now, in order, right, remember D2 was earlier holding some state from the previous evaluation. That state has changed and that now needs to be captured by the flop F2, F1, F2, okay. Flop F2 has to capture this new state appropriately, right? So, what I'll do is, I'll just put an event here. This event has reflected here and this event eventually reflects here. It is this event that has to be captured, not this one. Okay. So, in order for this event 1 to be captured, what is the constraint now? It should settle a setup time before the next clock edge. So, therefore, this has to be T setup, correct? This is your clock period. So, what is the constraint now? Yeah, right. So, let me write TC here and I'll write the sum of these delays, okay, which is basically TPCQ plus T what? PD plus T setup. What's the inequality? Greater than or equal to. As long as the clock is faster than this, I mean slower than this period, right, or the delay clock period is greater than these 3 delays, your system will function correctly. Okay. So, what does this mean? It implies TPD should be less than or equal to TC minus TPCQ plus T setup. Therefore, this constraint that we derived just now is called max delay constraint. It's the maximum delay that the combinational block can introduce without causing a failure in the system for a given clock period. So this is basically called max delay constraint. Okay, and this ideally, if my flops were so perfect, I didn't have a setup time and clock to queue delay and all that, then the entire clock period should have been available to me. I should have been able to use the full clock period to do my combinational circuit evaluation. But that's not possible. So this is called sequencing overhead. Okay, we'll see next when we do pipelining. When I remember earlier also when I discussed the idea of pipelining initially, I told you that you cannot just keep adding sequencing elements and make it faster and faster. You cannot improve the throughput continuously, right? Because you have a concept of a sequencing overhead, and that is essentially the setup time plus the propagation clock to queue delay. Okay. So now what happens is, maybe I should just discuss that right away. These two clocks, right, to F1 and F2 are coming from different points on the clock distribution network. Okay, so how does clock distribution happen? Let me show you that very briefly here. Okay, so what you do is, the clock generation happens at a central point in the chip, because the clock has to be insensitive to temperature, voltage changes and all that. So you make a PLL based clock or something like that, which is very stable, right, has no jitter, right. What is jitter? Basically the clock edge just moves around a little bit randomly. With time, one edge can go this way or that way, right. So you want to design something with low jitter and all that, and then you distribute this clock through the entire chip in a tree-like fashion here. So what is shown here is the clock is generated at this point, and I just route it through inverters in this fashion, right. So the nodes 1 to 8 are my leaf nodes where I am going to connect flops. Okay, in this example, of course, in reality, it's like, millions of nodes. So distribution network is a very complicated thing, but the idea is to ensure that the delay on any path is basically the same. Okay, you can optimize this delay, you can make it lesser and all that. I don't want, it's not necessary that the clock at node 1 and the clock at the origin should be in sync. That's not necessary. Of course, there will be a delay. The clocks at all these leaf nodes should be in sync, because that is what is going to control all my flops, right. So we safely assumed here that this phi, which is driving flop F1, is also driving F2 without any sync problems. That's why we drew only one clock. Otherwise, I should have drawn phi 1 and phi 2 and delayed them or something, right. So ideally you want it to be like this, and that's how you will design it with your clock distribution network. So if you take this network here, all paths are the same. If you ensure that the layout also is symmetric across all of them, the delay will be the same. In simulation, when you try to simulate this, you will see that the delay at all leaf nodes 1 to 8 are exactly the same. There is no problem. However, when you manufacture this, quite obviously you are going to have some process variations. All these inverters will not be identical to each other, right. And also spatially, if you look at this distribution network over the entire chip, one end of the chip may have a slight bias with respect to process parameters with respect to the other guy. So all these inverters may be slightly different from all these inverters. That's also possible. Apart from random changes, even systematically you could have some variations. Okay. Now because of that, I have to deal with what is known as clock skew, right. clock skew is basically the clock edge can simply now start varying randomly about these points. Okay, so what is clock skew? What is the exact delay here? It's from the reference clock edge. Where does this thing move, right? So for example, so I have shown you a band of curves here, right? A family of curves. Clock skew is basically the worst case delay. What is the worst case offset that I can have? That is called clock skew. T skew. Okay. Now I want to alter my timing constraint so that I am able to incorporate this skew as well. What do you think will happen? First of all, before you start this analysis, you have to tell me which case should I consider. Should I consider the case where the clock edge moves this way, or does it move this way? It moves to the left, right? It has to move this way because it has to eat. If it arrives later, then I have no problem because my data is anyway being set up with respect to the original clock edge, and this thing has got delayed, so there is no issue. If it comes inside, then I have a problem. Then what is the thing that gets altered in this diagram? T setup becomes with respect to what? The skewed clock, right? So with clock skew, this has to be T setup. Right? And of course, the delay from here to here is T skew. Right? So, how do I modify this expression now? TPCQ plus TPD plus T setup plus T skew. Right? And therefore, here also it will simply get modified as plus T Q. Okay, and of course this whole thing now is called sequencing override. Yes. D1 it arrives. So like I told you, the reference you have to make with respect to one clock. So like I told you, my reference clock is not this clock. It's not with respect to this clock that the leaf nodes start deviating. This guy, clock 1, the flop connected to the node 1 will become my reference clock. With respect to that, what happens to the next node is what we are saying. So what you are saying is, what if this guy at F1, it arrives late? Yeah. So, okay. So if this arrives T skew later, right? So question is, should you count it twice or not? Exactly. So it's just a question of counting it as which one you take as a reference, that's all. And T skew I think it just boils down to what you define as T-skew, right? That worst case number is with respect to one reference clock, where do these edges move, right? Correct, correct, yeah, correct. Between any two clocks, right? Yeah, therefore then if I consider T-skew here once, I'm done. Because I've considered between any two random clocks, this is the maximum number. Right? So you could divide it as T-skew by 2 here, T-skew by 2 there, doesn't matter. But it's just one counting. Yeah, correct. So I think that's right. So what he's saying is the T-skew definition is the worst case difference between any two clocks on the leaf nodes. That's what is T-skew. Okay, so that we have taken care of. Okay, so now what I want to do is I'm going to consider the following case now. Next, D1, Q1, then I have the combinational block delay, TCD, TPD. Okay, now I'm going to look at the case where data can race through, right, and affect D2, right? This is D2 in the same clock edge, right? I'm not waiting it for it to go, and so like I told you here, D2 was maintaining some earlier state, right? And that needs to be captured by the flop F2 and it needs to be held for a whole period and all that, right? But what if data from D1 races through and affects that earlier state that it is holding, right? That's also possible. So the way we analyze that is we bring this flop back here, okay, just notionally. This is Q2. Okay, this is again 5, 5. Right? So what I'm doing here is my clock is going high. Forget about the other edge. Okay? And data on D has changed. Okay? This is D1, this is D2. Right? Q1 changes, starts changing at T, C, C, Q, right? So you look at this. Okay? And D2. Where is D2? It is going to start changing after T, CD from TCCQ. Correct? So the earliest change will happen here. Okay? So T, C, C, Q. Then from this edge you can have T, C, D. Okay? Now, earlier in the previous cycle, right, D2 was being, at D2 there was some earlier value that had to be sampled. Okay, so if you look at the D2 guy, this is some value. Okay, let me call this event 2. Event 2 has happened here, event 2 has happened here. Event 1 is what was sitting on D2. Okay, and that needs to be sampled for the flop F1 to hold it correctly. Okay, remember I am talking now at this rising edge itself. So the event 1 actually needs to be sampled and held there correctly. The event 2 should not race through and overwrite that data. Now in order for D2 to sample event 1 that you see here, what is the constraint that I have to ensure? I have to do a hold time, right? If D2 changes before the hold time, then I have an issue, right? That's the basic point. So what is the constraint that I can now impose? This guy here, this delay in the worst case should be T hold. So therefore I can now write T hold, and I have two delays there, TCCQ and plus TCD. What's the inequality? Yes. As long as the hold time, as long as the data change happens after the hold time, right? So if this is my hold time, right? So let's say that, this is the worst case hold time, but let's say the hold time of the flop is somewhere here. Let's say this is T hold. As long as this change happens later, there is no issue, right? And that's what we are saying. So what does this mean? It implies that TCD should be greater than or equal to T hold minus Q, minus TCCQ, correct? So this is called a min delay constraint. Min delay constraint. The combinational block that you put between two flops should have a minimum delay so that you don't end up with a hold time violation, right? Correct? Now let me ask you this question. Suppose there is a setup time failure. What will you do? Suppose the setup time fails after you design the system, something happens, you are getting a setup time failure at the clock. Increase the time period of the clock, right? When we derived the max delay constraint, we said TPD was less than TC, clock period, minus some overhead. Unfortunately, in the min delay constraint, you don't have that luxury. You do not have that luxury of the clock period. Remember, after the chip comes back, this number is fixed, this number is fixed, this number is fixed. It's determined inside the chip and you are done for. So you have to be very, very careful about hold violations. If at simulation or at design time itself you figure out there's a hold violation, what should you do? Add buffers and increase the delay of the combinational block, right? That contamination delay you should increase somehow. Add some buffers and you can solve that problem there. But after the chip is manufactured, nothing. Okay. On the other hand, if there is a setup time violation, you can reduce the clock frequency and make it at least work, right? You may not be able to sell it appropriately for enough profit, but at least you can get it to work. You won't lose your job, right? Hold time violation, you'll surely lose your job because you have to dump that whole chip and the entire lot. Forget just that chip. Okay, so you have to be very careful about this. Now, as usual, we have to now incorporate clock skew into this. What happens if the clock edge moves around a little bit like this? First of all, which edge should I consider? Worst case consideration is the edge moving to the left or the edge moving to the right? To the right, because I now need to ensure that D2 is held for long enough after this edge, right? So this, if you look at this delay, it is T skew. From there, I need to ensure that there is enough hold time. So how do I modify this equation? First equation here, 1, 2. Where should I add T skew? To the left. So what is the net thing now? I will add T skew. Okay.